Okay, good morning, everybody. I warmly welcome you to the day 2 of OURS 2020, our annual research sessions. We will begin the day with an interesting keynote speech by Dr. Pratap Singh Dharmavansa from Department of Electronic and Telecommunication Engineering, University of Moratuwa. I now invite Dr. Uppala Premaratna from OUSL's Department of Electrical and Computer Engineering to introduce the keynote speaker and to invite him to deliver the keynote address.
A very good morning to all of you. I warmly welcome you all to the keynote address on the second day of OUSL Hours 2020. Our speaker today is an eminent researcher and a passionate academic. Dr. Pratap Singh Dharmavansa received the BSc and MSc degrees in Electronic and Telecommunication Engineering from the University of Moratuwa, Sri Lanka, in 2003 and 2004, respectively. He received his doctoral engineering degree in Information and Communication Technology from the Asian Institute of Technology, Thailand, in 2007. Subsequently, he joined the Department of Electronic and Computer Engineering, Hong Kong University of Science and Technology as a research associate. From October 2011 to 2012, he was with the Department of Communication and Networking, Aalto School of Electrical Engineering, Aalto University, which is formerly known as Helsinki University of Technology in Finland. He also served at the Stanford University, California, USA, during the time of October 2012 to August 2015. He currently serves as a senior lecturer in the Department of Electronic and Telecommunication Engineering, University of Moratuwa in Sri Lanka. He's also a visiting lecturer at the Department of Statistics of Stanford University, USA. He currently has 24 journal publications in reputed Q1 ranked journals, of which 16 are first authored and 23 conference papers, including one that won the Best Paper Award in Communication Theory at the flagship IEEE ICC 2011 conference. And he's also part of the IEEE Communication Society. He serves as an editor in IEEE Wireless Communication Letters, which is a Q1 ranked journal. And his research interests are in signal processing, random matrix theory, wireless communications, and high-dimensional statistics. So I warmly welcome you, Dr. Pratap Singh Dharmavansa, for the keynote session today, and over to you to deliver the speech.
Thanks, Utpala. Excuse me. Thanks, Utpala, for a very detailed introduction. Hello, everybody. Good morning. Hope you are doing well amid this lockdown situation. Let me try to share my screen with you. First of all, I may switch off my video because the thing is internet connections are so speed in this country. Because of that, there can be finite many discontinuities. To facilitate the efficient utilization of the bandwidth, though, what I'm going to do is I'm going to switch off my video streaming, and then I'll share my screen with you. Can you see my screen though?
Yes.
Okay, great. Good morning, everybody. Thank you for the feedback, because from my end, I cannot see anything. I can see only my screen. I'm not sure whether you can see it. Okay. My topic is the past and present of the linear model. So I thank you very much for the organizers of OURS event for inviting me to give this talk, which is relevant at this time and which is might be very useful actually. Let's move on with the talk. Let's see. Okay. So I start with famous saying by two famous, one is statistician and one is a mathematician, a stochastic analyst. George Box is British-born American statistician who founded the Department of Statistics, Wisconsin, I suppose, medicine, or can't quite remember now. He says, essentially all models are wrong, but some are useful. It's a very strong statement, actually. That means we, day-to-day life, we use a lot of models. What he says is, all models are wrong. So we try to approximate the phenomena with certain models, actually. In that aspect, actually, some are pretty useful, whereas some are not useful. In contrast, Samuel Collin at Stanford University, he's a Polish-born American, he's not a statistician as such, he's a mathematician. He said, the purpose of model is not to fit the data, but to sharpen the question. It's quite important what he's telling. You should not believe in your model as such. You should not indulge in your model, and you should question your model, actually. So sharpen the question is you have to reform the model, actually. So you can see these famous people, they are all in a view that models are pretty useful, but when you try to interpret them from the correct perspective. However, if you indulge in the model wrongfully, you might get come into wrong conclusions. Now, moving forward, this is the model that we are going to discuss today. The main theme is the linear model. Now, you may wonder why this guy's going to talk about linear model. Everybody knows linear model. Every Tom, Dick, and Harry in the town knows it. Yeah, you are correct. So it dates back to Legendre and Gauss, almost 2 centuries old, more than 2 centuries. And it's come to Galton, the famous sociologist, in 1875, and it propagates to modern era. You can easily see the lineage has not been broken. It's still going on. What makes it so useful? I'm 100% sure most of the people in this audience, at some point in their life, they must have seen this one or must have used this one for their research work or interpreting something, or at least to teach somebody, or just for the sake of earning grade for a particular course. Now, let's go beyond that. This model is very simple, extremely useful, and have certain optimal properties. Otherwise, it cannot survive for such 2 centuries. It cannot survive 2 centuries because the other model would have easily taken over the place, and this model must have been replaced, but it did not happen because it's simple, useful, and have some certain optimal properties that I'm going to discuss shortly. Now, why do you think it's useful? Well, one thing is like it can summarize data very nicely. You are going to see these things. On the other hand, it can be used to predict. Of course, prediction is very hot topic these days with machine learning community. It's prediction. They talk about prediction always. And not only that, actually, one of the most important things of the linear model being you can think about, you can quantize the result of intervention in causal inferences. Subject is causal inferences. Now we have to be careful in this aspect, actually. Linear model can be used to make causal inferences, but not always. In certain situations, the causality can be inferred from the model, whereas some certain instances, you cannot infer causality. Now, going through this one, you can easily see this linear model is looks pretty useful. It looks like it has been tested more than 2 centuries, yet it has its own identity, and yet it survived and continue to survive. Now, against this backdrop, we are going to talk about in this discussion or this talk. In the beginning, I'll talk about the classical viewpoint of linear model. What is the classical viewpoint? You must have learned this thing for your undergraduate or postgraduate, or you must have learned this most of the techniques. You have to bear with me, actually. But then I'll give you the modern view of linear model. How does the model change? How does the assumption changes over the time? And then I'll conclude with conclusive remark. Now, moving on to classical viewpoint, I'll focus, or I'll draw your attention to one of the most famous studies in social sciences, extracted from Friedman's famous book on linear model. This is called Pearson and Lee data, 1903. Pearson and Lee, two researchers, they wanted to measure the correlation. They want to identify the trend between the heights of fathers and their respective sons. So this is called father and son data. So for the sake of visual purpose, actually, I have basically obtained the scatter plot using R. this scatter plot, if you look at carefully, preliminary observation, you can easily see there's a positive going correlation between son and father's heights. By the way, heights are in both in inches. Forgot to mention from my side. I'm sorry for that. So you can easily see positive going correlation. But the important thing here is though, if somebody asks the question, if you fix father's height at 65 inches, you can ask a meaningful question like, what would the average height of son be? What would average height of sun be? Now, if you draw a vertical line crossing 65, you can see there are so many points cutting. So sort of you can talk about average actually. Sort of you understand when you look at this model, you are basically you are basically sample from bivariate distribution in a way. Okay. But the salient point here is this experiment, you don't have much degree of freedom. You cannot intervene with this experiment, this observation study. You can't intervene. You can collect data and come to your office and then you can plot to analyze and things like that, but you can't intervene in the sense that you can't go to the field and find exactly father having 70 inch height and corresponding son height. You don't have that luxury. You can collect data and then you come and try to make inferences. In contrast though, if you look at this physical science experiment, this is a response schedule. The Hooke's law experiment, you know very well that when you add force to spring in the elastic region, the extension is proportional to the weight. And you can see weight and length scattered plot. But here, there's a subtle thing you can observe actually. So you have flexibility of changing weight as you wish, and corresponding length you can measure actually. So you have degrees of freedom here. You can intervene. You can intervene at any point and you can change force. My choice is 6.5 kg. Okay, you can choose it. It's highly controlled. This is known as response schedule. You can see corresponding to one weight, exactly 1 point. Okay, this is known as a response schedule actually. If you move forward, you can easily see there's a stark difference between these two experiments. First one is observational study, whereas the second one is response schedule. First one shows the association between quantities, whereas the second one shows the causation actually. So the first one, you can't do intervention though. First experiment, you can do selection. The second one, you can intervene and you can say, okay, I'm going to set 6.5 kg and I want to see the respective outcome. In the first experiment, you don't have, because largely it's observational. You can't do much about observational studies actually. And the most important thing about these two models are confounding versus functional relationship. Confounding is very critical thing, especially once you do social science experiment and things like that. If you attribute to outcome to your features that you have already chosen, if you try to explain, sometimes you cannot explain outcome using your features somehow or the other. So more often there are confounding factor. That means a factor which affects outcome, severely affecting outcome, but which is not in the main effect actually, which is not the main reason, or not because of the treatment. So whereas this response schedule is a result of a functional relationship between the output and input variables. Now, having said these things, you can easily see everything depends on the assumptions you make behind the linear model actually. Model is very interesting. You can see y equals, first part is known as systematic part. The second one is unknown errors. So you have to make certain assumptions to make sure this model is working. Depending on the areas, assumptions are going to be different, but in general, these are the assumptions that we are going to make. First, data. Let us assume that we have this kind of data set. So y1 corresponding output corresponding to x11 up to x1p, and such n data observations are there. You can easily see this thing. So you can succinctly write them using n simultaneous equations, like the form that is shown below. Now, this is cumbersome actually. This is not the way exactly people would like to see, because there are so many summations and indices, and it's highly likely that you go mad soon. So let's clean up the house. So to clean up the house, let's go for matrix representation. So you stack all observations into boldface Y, and all the parameters that you are going to interest in your model beta into one vector. And your design components, actually we call it covariates and all sort of names, into X and P, and all the random errors are stacked into one vector. Here's epsilon, actually boldface. Now this is the most dearest linear model actually. Now Y is known as response variable or dependent variable or output, sometimes people call. X is a design matrix. Usually we call design matrix actually. and beta is regression parameters and random errors. Now here, one thing important to mention is beta and epsilon are not observable quantities. This is the model. We believe that output can be adequately explained using this linear structure. Now, there are some assumptions in order. So all epsilons, that means all error terms are IID, identical and independent distributed random variables. You don't need Gaussian assumption though. Having said that, we can mathematically say expected value has to be 0. And the covariance is basically sigma square I form. That is, we say homoscedasticity in the sense that across all error terms, error term 1 to error n, they have the same variance. The opposite is heteroscedasticity. Heteroscedasticity means like basically different error terms have different variances, on which I'm not going to talk about. It's called generalized linear model. Moving into N and P, the classical statistics is heavily rely on the number of samples, independent samples you collect N has to be much greater than the features number P actually. So N is greater than P. And furthermore, we assume that rank X is P, the rank of the matrix is P. What does that mean? I read mathematics. Rank of P means basically the columns of X are linearly, not linearly correlated actually, or not linear combination. One column is not a linear combination of other columns actually. So we believe it's full rank. And the last assumption is quite important. If X is random, in some experiment, X is going to be random, and epsilon is independent of X actually. Okay, so it's called exogeneity, or there's another one called endogeneity. If X is correlated with epsilon, which is which often arises in econometrics, they call it instrumental variable, or we call it two-stage least squares, on which we are not going to talk about in this talk. So we are talking about very simple model, y equal x beta plus epsilon with these assumptions. These are fairly general assumptions that you make. Probably you did not know this assumption, or probably you were aware of this assumption, or you didn't pay much attention, but still you run linear model. Nonetheless, these are fairly standard assumptions, dwelling on which we try to make statistical inferences, or try to predict and things like that. Now, the next emerging question is like, what's going to be beta? So how do you find beta? Because beta is unobservable, however estimable. So if it's unobservable, but it is estimable, why don't we go and estimate it? So this is called least square estimators. So you minimize residual sum of squares. Don't pay much attention to mathematics. If you go here, you can see the beta hat. Beta hat is least square estimator. It's a linear estimator, linear in Y, non-linear in X. Doesn't matter. Because you know X, your design matrix you are aware of, and you know Y, your observation, you can right away find beta hat, a matrix, vector. Okay, now you can decompose beta hat into beta plus something like this. Now this shows clearly that what's estimated beta inside true beta is there. True beta plus some random fluctuations. True beta plus some random fluctuations are there. So this is how it is. Now here there's a dangerous element, x dash x inverse. Now for small size, like if P features are like 5, 6, 7, 8, 9, 10, probably x dash x inverse is like a very efficient calculation, you can do it. But imagine a situation where feature space is like 100 dimensional or 1000 dimensional. Then we know that if you want to do matrix inversion, it's a or n3 operations. Like if 100 is like 1 million operations should be there, you have 1000 dimensional feature space, it should be 1 billion operations should be there. It's going to be very expensive numerically. So what can we do about that? Well, the machine learning community use so-called you use algorithmic implementation called gradient descent method. So what you do is you start with a typical beta node, beta sub 0 basically, and then you iterate this one till converges. This is called gradient descent algorithm. So here there's no matrix inversion, so you can avoid that one. And this algorithm under certain situations, the alpha is known as learning rate sometimes. There's a theory behind it, very beautiful. It's going to converge. And I'm going to tell you that this optimization problem is unconstrained. It's a quadratic unconstrained optimization problem, which is convex. So it's a guaranteed that you have efficient algorithm to solve this one. This solution is, this algorithm is to guarantee to converge to solution. Okay, so you can see now earlier this is mathematically beautiful result, but you can't do much you can't do much practical thing with this one because it's going to be scary when the dimensionality is getting larger and larger. So to circumvent this complexity, we come up with this algorithmic implementation. Now let's see a little bit about values that structure of this problem. So y hat is fitted values equal x beta. Or in other words, you can simply say h of y. H is quite famous matrix. H is rank efficient and it's an idempotent matrices in the sense that if you square h, you get h. If you raise any power h to any power, the answer is going to be h. It's so funny. And then what matters is residuals. Residuals is the way that a proxy to understand the behavior of random errors. So if you calculate residuals, the difference between observed value and fitted values, y minus y hat, you can write like this, in minus h epsilon mathematically. This is not the interesting thing. The interesting thing is, if you consider the residual correlation, it turns out that it has non-zero correlation. The matrix, there's a matrix, correlation matrix exists. So what does that mean? That means although we try to understand the behaviors, random errors through residuals, that's the only way we can understand, the only proxy that we have, but it turns out that it's not going to work like that, because the thing is like errors are always correlated. So this is one point to think. Then there's something called multi-collinearity, in the sense that if one or two columns of X are like linearly correlated, then what's going to happen is the model is going to break down. So how do you find it? Well, you can use a so-called condition number, lambda max and lambda min of X dash X to figure it out. And you can calculate any dimensional matrix, lambda max and lambda min efficiently. Now, if you omit all mathematics detail, actually what we are going to do is like, we have n-dimensional data vector and you have p features. So you try to explain the things in n-dimension, variability in dimension using p dimensions, and try to ascribe the unexplained amount to n minus p dimensions, so we call random fluctuations. Now, if you move forward, there's a very beautiful geometric interpretation to this one, extremely beautiful. This parallelogram represent span, in the sense like all linear combinations of columns of X, and then your Y protrude out from this subspace. And what exactly you are doing in the linear model is you project this one onto the subspace. X beta hat is exactly the projection, actually, exactly the projection. And then the question comes, actually, how good this model is, how well the data fit to model, how well, I mean, all this nonsense mathematics, how well. So it's coefficient of determination, or we call it goodness of fit, it's R square. It measures the variability in your estimator, y hat, fitted values variability, variance, divided by the variability of the original data set. So it has to be less than 1. But if it is pretty close to 1, it does not verify model by any means. It shows that there's an association with this variable. A counterexample comes from Friedman's book, like 1950 to 1999, purchasing power of the US dollar and the death rate from lung cancer. If you regress on each other, it turns out that R square is 0.9. But everybody knows that purchasing power of dollar neither increase death rate nor prevent lung cancer, nor prevent lung cancer either. So you can easily see two variables are like upward trend or downward trend. You can easily regress, but you have to be really careful when you try to interpret them. Now you can see this geometric interpretation is not common to or not only restricted to linear model. Here is far-reaching consequences are there. These kind of models are there for Fourier analysis. Those who are not, you given function y, imagine, and then you project onto infinite dimensional Euclidean space or Hilbert space, and the Fourier basis is the basis for Hilbert space, and people are aware of this one. So the same intuition, same intuitive idea is behind that. Okay, so moving into the next slide, we can see what are the optimalities of beta hat. So optimality, then the Gauss-Markov theorem kicks it. It says that among all linear unbiased estimators, beta hat least square has the minimum variance. This is a very strong statement. This is the exact reason why this survived. That means basically, if you are ready to violate linearity or unbiasedness, you can reduce more variance. You can find estimators which are nonlinear, either nonlinear or unbiased estimator, which has a minimum, which has lower variances than least squares. That's always possible. But if you are in the sphere of linear unbiased estimators, least squares estimator is the best actually. This is what he said. This is a very strong statement. The statement itself doesn't catch its meaning the way I wrote it, because it says that B hat has the minimum variance. But if you are really careful about beta hat, you know beta is basically a vector. Vectors cannot have variances. It should have covariances, as I mentioned here. Vectors cannot have variances actually. But this is like a colloquial way or like layman's way of telling this, presenting this statement. But a statement you try to understand qualitatively, like if you can find, you cannot find another linear estimator which somehow or the other induce smaller variance than what is promised by least square estimator. So this is a very strong theorem, Gauss-Markov theorem. And E beta hat is basically beta. You can easily show this is called unbiasedness. That means on average, beta goes to beta on average. Okay, this is a stochastic convergence statement, but this is exact statement. E beta hat is beta, and the covariance is given by this. You can see covariance depends through x dash x inverse. Okay, this very dash x inverse is not through x dash x inverse. So if you happen to have some sort of multicollinearity problem, then you cannot invert the matrix and you are in trouble. Okay. Now, next what matter is like beta as a matrix that you have individual components. So you can write confidence intervals for that one. So this is a two-sided T confidence intervals, individual one. But since beta is a vector, you can write confidence ellipse using F-test as this. And sometimes people might think about confidence ellipse is like a structure, basically a geometric structure, ellipsoid basically, and individual are lines. So typically a confidence ellipse gives the best idea about confidence of particularly choosing one particular beta, but individual terms are also okay. But sometimes you find simultaneous confidence intervals, they are much wider than this one. But if you want really a good correction to the simultaneous observations, what you can do is you can go for Bonferroni correction, if you like. So typical simultaneous confidence intervals that you obtain projecting ellipse onto respective axis are much wider than individual CIs. That's how it works actually. Now you can see entire picture is here, like Gauss-Markov theorem promised something to you. This works according to that one. But now what happened is people are thinking like, oh, okay, can we trade unbiasedness a little bit to achieve variance reduction? This is known as bias variance trade-off. This very important topic is modern machine learning and statistics. Can we trade some unbiasedness? So you are lenient on unbiased. Okay. Let me think linear estimators. No problem. I don't want to violate linearity. Linearity is still there, but I'm more than happy to sacrifice a little bit of biasness. So it's unbiased. So can we see some estimators? Can we find some estimators which are biased, however linear, and you can get large variance reduction? Answer is yes. You can violate both linear and unbiased, both you can violate as an answer is yes. And this will drive you to the modern era of linear model actually. Having said that, I want to tell this works for old era as well. These new models, new inferences, and new estimation technique works for all the models as well. That's not a problem, but it's more relevant to the modern linear model. Then you may wonder, what do you mean by modern linear model? You always tell linear model, modern. I mean, what's the difference? I mean, linear model is linear model. It's not gonna change, right? What is this big fuss about model linear model? Now, to understand model linear model, actually, first we have to understand so-called high dimensionality. So let's look at the modern view, high dimensionality. So understand high dimensionality, we have to see that according to today behavior of people actually. So imagine every time you take your mobile phone, some of which you may be doing right now, and touch the screen and demand for some data. At the very same time you demand data, you subscribe data. At the same time you create data for somebody. So this is like full duplex work is going on actually. So you demand data at the same time you create data for some party. Then privacy issues, everything comes because you demand and then you give some data to them. So this is exchange process actually. So thanks to this exchange process and thanks to the development of computer era, computational complexity went down and computational cost is very low. And we are willingness or unwillingness, we are creatures now consuming a lot of data at the same time creating a lot of data. So you have like hard disk, so many hard disks, and you are going to run out of hard disk space, and then you want cloud, and never ending desire for data, never ending desire to save the data. So what can you do with data? Okay. So these are the mechanisms that generate a lot of data. DNA sequencing, one of the most important things these days you can see with this COVID situation. Internet portals, financial data, particularly high frequency data, tick by tick data. You are going to, at the end of the day transaction, you can find a lot of data, and satellite imagery, consumer financial data, and sensor networks. Through all this mechanism, actually people start to create data at unprecedented rate. Now, the most salient feature of these data sets, in contrast to ancient data sets, are high dimensionality. What does that mean? That means large P. The number of features that you can collect has already exceeded the number of samples. Put it in this way. There are some cancer patients, rare cancers. You can find a handful of patients But if you get the genomic sequence of this, when genomic structures, you can get tens, hundreds of thousands of genome data for a person actually. So one person new feature space is probably 100 or 200 or 300, whereas such how many people are there? Probably 10, 15 people are there. Now you can see the number P is larger than N. On the other hand, sometimes if you go to this internet data and all sort of data, sometimes P and N are proportional. So P, N is 1 million, P is probably 500,000. It's a proportional. It's going to be proportionally somehow or the other sense, same order of magnitude actually. Or if you look at some sort of experiment that you are conducting with diamond, say for instance, for diamond, I mean, you cannot have like hundreds of thousands of diamonds to break if it's an invasive experiment. You have a limited number of samples, but you can take so many experimental measures on a given diamond. So you can see, depending on the state, depending on your requirement, actually, the number of N and P somehow are going to change. The dimension is going to change. Now, one of the salient features in modern data sets are high dimensionality. That means we call it simply large P error. That means P is greater than N, or P is proportional to N or greater than N. Now, this poses unprecedented challenges to statisticians and all other people. Now, moving on, there's a one very famous name synonymous with high dimensionality. It's called the curse of high dimensionality, or curse of dimensionality, coined by Bellman in 1961. Now, if you omit this first statement, which has something to do with product spaces, let's look at machine learning view. Machine learning people say local methods fail in high dimensional setting. That means like machine learning, you have some local methods like non-parametric method, like a nearest neighbor method. You just classification, you just look at the nearest neighbor and you classify the center according to that one. So it says that when the dimensionality is getting larger and larger, the nearest neighbor methods are going to fail actually. These methods are not going to be nearest neighbor. Now to motivate this one, we have this cooked up example actually, this toy example. Assume that you have a data with respect to certain point, you consider a hypercube, p-dimensional hypercube around that point. And your objective is to capture R fraction of observations. You have some sort of observations here. You want to find certain percentage, like a 10% of data, 10% of entire one around you neighborhood. You want to get 10% or 1% because that is nearest neighbor. And if you do like that, you can see the edge length become R1 to the power P. You can do simple calculation. And that's not the idea. The idea is this: in the 10 dimension, if P is 10, to capture 1% of data, you have to take 63% of each variable, each dimension. You have to at least cover 63%. The things are going to get worse. If you need 10% from each variable, each dimension, you have to at least search for 80% of each variable dimension. Now, if you look at carefully here, like you are talking about nearest neighbor, but when the dimension is getting larger and larger, the nearest neighbor, I mean, it becomes no longer nearest neighbor. It's like farthest neighbor, it seems to me like. Because you are going far away from your domain actually, because you are center, you have a small cube around you and you want to capture R fraction. But if you want to capture 10% of total data, which make perfect sense in 10th dimension, you need to search each axis, each data axis, if you believe their axis, each axis, you have to get 80% of each axis. That doesn't make any sense actually. It's not no longer local. Okay. Now let's see a graphical viewpoint of this one. You can easily see. This is P1, P2, P3, P10 dimensionality is getting increased. And you can see here it's crazy. Like if you want 10% of data here, fraction of volume, 10% of volume. So whether you like it or not, you have to get distance from that particular point, neighborhood, like 80 point. 80% of the thing you have to search. It's no longer local actually. It's no longer local. It's going to be highly global now, although we call it local method. Now you can see the local methods tend to fail in high dimension. But small dimension, it doesn't really matter actually. You can live with it. It's less than 50% for third dimension. You can see 3 dimension, less than 50%. I mean, you can live with it. Not a problem as such. But when dimension is getting larger and larger, actually, it's pretty uncomfortable thing. Okay, so P is becoming larger than A. So this is it. So now, what's the effect on linear model? Linear model fails. Not linear model fails exactly, actually. Linear estimation method fails, actually. So you need to have x dash x inverse. Now, if P is greater than N, we know that x dash x is rank deficient. If it is rank deficient, that means x dash x is correlation matrix, highly correlated actually. The features are extremely highly correlated in your language. If they are extremely highly correlated, if you estimate if n is greater than P is greater than N actually, the correlation matrix that you try to evaluate is a garbage basically. X-X is completely garbage, not high quality. As such, X-X inverse does not exist and is utterly failure. So in high dimensional least square estimators fail. But are we done now? No, we are not done actually. Then the concept of shrinkage and regularization kicks in actually. Let's see what does that mean. This ridge estimator, probably you are familiar with this one, found in 1970s. What they do is like a very smart thing. You get least square estimator, the same least square minimization part, plus you put some L2 penalization. That means basically you have restriction on the earlier there was no this part, and what you were doing is like basically you were solving unconstrained optimization problem. But here sort of constraint, if you can write the equivalent form, actually you can easily see is a constraint optimization. You constrain on the Euclidean norm square of data. So you are trying to estimate some parameter, estimate a vector, and then in linear model, least square, you don't pay much attention to the size, but here you pay attention to the size actually. Fortunately, it's a linear estimator. You can see closed form solution is there. However, this is a bias estimator, and as such, actually, the variance is much smaller than variance promised by least squares actually. So this is immune to multi-collinearity because X-X you may or may not be able to invert, but lambda IP always invertible. And we call that lambda is the amount of shrinkage. That means the you are shrinkage towards zero, and we call it induces sparsity. Now, if you want to see really numerical example, it's like this. This right-hand side basically though, all are 8 variable regression. This is not a high dimensional, but normal dimension. These 8 variables are in the regression as such. These are the values. But if you choose a certain value for lambda using cross validation though, then you can see the parameters are basically shrunk. These values are here, they are shrunk actually. Some are of course put an emphasis, but some are shrunk actually, you can see. So this is called shrinkage estimators actually. Now there's another estimator, this one that's called LASSO, least absolute shrinkage and selection operator. Coined by Tip Shirani, Stanford Statistics through his PhD thesis. And electrical engineering community Chen is called a basis pursuit algorithm. It's very simple. What you are going to do is same linear model you take, and your penalization is going to be L1 penalization. That means absolute sum of elements in beta. So you do this kind of thing. And this problem is you don't have linear, you don't have a closed form solution, unfortunately. But lambda is control the amount of shrinkage to zero, not towards zero, to zero. You will see shortly. And there's no closed form solution. However, the problem is convex. You can solve efficiently. And optimum lambda you find through cross validation. And this not promotes sparsity. This induces sparsity for the model. So this is one of the most important model. And this works for p greater than n as well. No problem. So this is not a p greater than n1. This is some normal model. You can see the meaning of sparsity. You can see what's happening. So these are least square estimators. You have 8 estimators here. Once you keep increasing the shrinkage, you can see ultimately all the estimators, this Gleason goes to 0, H goes to 0, LCP goes to 0, PGG45 goes to 0, LBPH goes to 0. Ultimately, the remaining parameters estimators are basically this 3. You start with 8 and you found already 3 non-zero parameters. So you can easily see this does variable selection and estimation at the same time. One stone, two birds. This is pretty smart actually. You can do variable selection, which is very controversial in variable selection in linear model, linear regression. There are so many algorithms. No one knows what is correct, what's wrong. But here actually, in some sense, shrinkage to 0, this is going to somehow or the other do the variable selection and estimation at the same time. So this is very efficient. It can be used for n greater than p as well as n less than p. Utility is pretty high and used across wide areas of sciences right now. There are variants as well for this one. Okay, so these are called lasso paths. This is basically two-dimensional geometrical characterization of lasso actually and ridge. The ridge actually is basically your constraint set is like a convex circle in 2 dimension, and you find this point. You try to find this point estimator which satisfies this one. This beta hat is least square estimator. You can see the bias. Vector beta hat is here. The estimator from ridge is somewhere here. So there's a bias, and you can see shrinkage towards 0 because beta 1 is pretty close to 0, whereas beta 2 is not. In contrast here though, is still convex structure. You have convex constraint set, but then you can see this is going to hit this particular tip actually at this particular tip. So beta 1 is 0, whereas beta 2 is non-zero. You can easily see it basically induces sparsity for your solution. So the sparsity is quite important in the 20th century Sparsity is quite important in the 21st century topic, actually. So you want to find solution which is sparse. So this lasso and everything works pretty much efficiently for very sparse estimator set. If you know that the thing that you are going to find is pretty sparse somehow or the other into certain basis, you can efficiently find this thing using lasso and reach, actually. So this is a basic idea of the geometrical characterization. This concentric cell ellipses are basically on beta 1, beta 2 plane. Actually, if you can remember confidence ellipse, these are concentric ellipses. Actually, for these are basically RSS same surfaces are ellipsoids. That's you understand. Now this is not the end, actually. Beyond ridge and lasso. So what people have done is basically they use least square part intact, but then the penalization they change to any qth norm of a vector. Well, two-dimensional characterization, Q1 we know basically is the diamond shape. Q2 we know is a square, circular shape, but Q4 is like a funny shape. It's not a square, but looks like a square. Or Q is 0.5. This is like a cusp here. It's a very strange shape, and Q.1 is a bizarre shape, actually. Now you can see this Q less than 1, actually, these norms are not convex. These structures are not convex. They are non-convex sets, but here things are all convex sets. So this thing solution is quite standard because convex solutions are there, but this part of the world, actually, the solutions are not convex. Now, what are the competitors for linear model? All this lasso and beyond lasso. So the least angle regression found by Bradley Efren, the person who found a resampling method bootstrapping, and dancing selector Candice and Tao. Terence Tao is the is UCLA mathematics. He's the youngest field medalist, the highest honor that a mathematician can get in his lifetime. He got it. He's a mathematician. Candice in Stanford statistics. And all this L1 penalization, L1 minimization, all the things are recently captured by, not exactly related, but not non-related as such, one thing called compressed sensing. Candice and Tao first found it, and then Dave Donahoe, Stanford statistics, he modified this. This compressed sensing has been used for many applications in imaging, medical imaging, especially MRI scanners. The basic idea is like Shannon sampling theorem says us that if you wanna sample, reconstruct signal from samples, you have to sample twice at least the bandwidth. But the compressor sensing people say that you don't need that twice. If the signal is sufficiently sparse, you can reconstruct signal by sampling way below rate than promised by Shannon sampling rate. This is one of the most remarkable discoveries through which they reconstruct images using random samples, which is far below than what is promised by our Shannon. Now you can see easily all the things are entangled at some point or the other. So you start with basic linear model, very basic linear model you started with, everybody knows. But then you can see to which depth you can go and what are the things that you can find through that same linear model, it's slightly modification. In the high dimensional, it's gonna get worse sometimes, but you can see still the linear model survived 2 centuries, no wonder why. No wonder why it survives. So these are my concluding remarks. High dimensionality poses unprecedented challenges. So high dimensional statistics is one of the hot areas right now in the Western world people are researching on. Because classical tools fails, that's the exact reason. Classical tool miserably fails sometimes, but then you want to make inferences, but you have to be really aware of high dimensionality, because the thing is, right, if you appeal for hypothesis grow faster than the statistical strength of data, it's highly likely that you are making garbage hypothesis. That's the danger of high dimensionality, actually. You have so large dimensional data, actually the hypothesis cravings for your hypothesis is growing very fast than the statistical strength promised by data. All this data has statistical strength. Now, if you exceed that strength, you are likely to make inferences, you are likely to make conclusions based on that. It might be crazy, but yet you support your conclusion with data. Of course you can support, because you are not careful enough. Okay. So the last conclusion is actually you have to be really revisit linear model in the light of high dimensionality. There are so many things I omitted: variable selection, you know, how to verify model, all this Melos CP, the variable selection criteria, generalized least squares, and there are so many things I omitted because I don't have time to discuss these things. But everything boils down ultimately to this question: actually, what can you do in high dimensionality? There are several tools right now, as I have pointed out, but there are yet to be found. There are many researches going on, and this linear model is yet alive. very old yet alive topic. And then I have some references here. The first references is the element of statistical learning, data mining, inferences, and prediction. You can see this reference has been cited more than 53,000 now, because these techniques are useful across heterogeneous fields of sciences. Actually, doesn't really matter what you are doing. Somehow that is going to be useful. More than 53,000 citations. Can't imagine that. So you can imagine the citation number for these authors. The Rob citations are more than 398,000 as far as I can see now in Google Scholar. You may go and see. So you can see they are doing extremely useful thing to community. And then the statistical model theory and practice by late David Friedman, Berkeley statistician. He passed away in 2008. A linear model with Julian J. Faraway, quite accessible book, and it discussed a lot about linear model and how to use R and things like that. Okay, so thank you very much for listening to me. I don't know whether we have Q&A sessions. I'm very happy if we have Q&A session. If we don't have, if you want to send me emails or discuss anything, you can find easily my email address. Everything is in public domain. You are more than welcome to send your comments, queries, allegations, or suggestions, things like that to me. Thank you very much. And I would like to hand over connection to our community. Thank you very much.
Dr. Pratap Singh Dharmavan, sir, thank you very much for delivering the first keynote address for OURS 2020 Day 2. We will now gently move on to our sessions for the day. There will be 4 parallel sessions. The first parallel session will be led by Professor VPS Pereira on physical sciences. Professor A.S. Chandrabose will lead the session on humanities and social sciences, whereas Professor G.D. Lekamge will lead the session on education, and Professor V. Sivalogadathan on management. I invite you to go to the relevant session or the sessions that interest you and participate in the first Day 2 sessions of OURS 2020. Thank you.